one.
Yeah, there was another one? I don't know.
Oh, there was another
Meeting
one.
is now streaming live. Yay. I love that you can see the Phoenix lander if you look carefully way up near the North Pole there.
Mm-hmm.
And that was so poetic. It was up there and slowly was destroyed as carbon dioxide ice formed around it.
Huh.
It's kind of, there it is, way up at the top.
Yeah, way up the top,
Yeah,
Phoenix.
Phoenix lander. Unlike Spirit and Opportunity, which have gone for years and years and years and years before they failed. Phoenix was a one Martian year. There we are. We're on some of the live streaming services, which is great.
Let's see if Richard Grace beat everybody to the
Cameron
punch.
Gillis is on first.
Oh,
Yep. And then Brooke Davies.
I'm looking it up now.
Tyler, I love that there are people appearing in and out of your background, like trans-dimensional characters from
it never ends.
a
I'm
crazy sci-fi episode.
I'm highly sought after CSR rep. I'm telling you, it's ridiculous.
It's all good, man. It's good to be loved.
We'll go with that. So how's your observatory coming?
The observatory has kind of fallen off the table.
Oh,
We had, we had a nutty, crazy. We had a small home repair project
Mhm.
that ballooned to be several. It was
usually
supposed to be
how it
like
works.
$5,000, and it's ballooned to around 20.
Ugh, that's a big balloon.
Yeah. It was just like, can you redo the planking on our front porch and steps? And the guy we had was really good. And he said, oh, well, you know, your back deck is really, did you notice there's a slope on it here that the back corner is collapsing and the whole thing's going to fall down? Well, then we said, well, you better take a look at that. And then he said, oh, you know, they installed it wrong. Instead of nailing it, putting it on pylons, they nailed it to your wall and they punctured all your waterproof flashing. And look at the sheathing on your walls is rotting. And it's just turned into this giant repair nightmare.
Did you just tell him to stop talking after that one?
Well, I could have done that, but he does things like he showed me, oh, look, here's the posts that are holding up your front stairs. He takes his thumb and he puts it into the post up to his thumb, up to his first joint of his thumb. He goes, look, I can poke right in there. I'm like, oh, that's bad. He said, yeah, the whole thing could fall off. You know, you can have somebody walking up your stairs and the whole thing could collapse on you. Like,
Oh,
well,
mercy.
that's bad. And so I have a very nice front porch and deck now,
It's good.
sure you
which is
do.
good. And it's not falling off. And It's now installed properly, so it's not causing more rot at my house. Because and this stuff was original to the construction of the house. The people who built it, I don't know if it was do-it-yourself project or what, but yeah. And
How
the
old is
guy's
the
not
home?
just playing games. When somebody can take their finger and poke it into a 4x4 post.
It's a big guy.
Yeah, he's either secretly Superman or there's a real problem. And I could do
Yeah.
it too. So I'm like, yeah, that's bad.
All right,
So-
Scott, we're running 3 minutes over. All right, here we go.
There we are. We are ready.
Hey, it's just a fraction of the time span of the universe. Having said nothing.
Welcome to live program.
MAVEN is a spacecraft that's orbiting Mars. It's been there since 2014. MAVEN, in this case, is an acronym. It stands for Mars, Atmosphere, and Volatile Evolution. And this gives a clue as to what MAVEN's real goal is. It's to study the top of the atmosphere and how the gases in the top of the atmosphere might escape from Mars away to space.
So the atmosphere of Mars must have been a lot thicker about 4 billion years ago. And today it's very cold and dry. And MAVEN is meant to understand the atmosphere as it is today and how it has evolved into this current cold, dry state.
One of the things we're trying to understand with MAVEN is whether a magnetic field for a planet is important for regulating the climate or allowing the planet to keep an atmosphere. Earth has a global dynamo magnetic field. Mars does not, but Mars has an induced magnetosphere. It has an induced magnetic field.
The upper atmosphere of Mars is being ionized by solar radiation. And so the electrons are being stripped from the atoms in the atmosphere. When that happens, it turns into what we call a state of plasma. This plasma in the upper atmosphere is very conductive. It leads electric currents to flow through it. Electric currents, they shape the magnetic fields that are around them. And that's actually how we see them with MAVEN. We take magnetic field data and we map it around the planet, and from that, the currents emerge. We've known how the currents flow in the Earth's magnetosphere for decades, but we don't know how that works around Mars. We don't know how it influences the interaction with the solar wind, because it determines how energy is flowing into the atmosphere, how it's transferred from the solar wind into the system. And that's what we're trying to do with MAVEN. When you just look at the data as it comes down, you're just seeing a little squiggly line, essentially. You're seeing the magnetic field strength and its direction vary as the spacecraft is flying through different regions. And so what you have to do is you have to actually map it to the planet and to this interaction with the solar wind. And then it starts to emerge that you have a drape situation where the magnetic field of the solar wind encounters the planet and it starts to wrap around it. And the reason it wraps around the planet is those electric currents that we are seeing.
The magnetic field in the solar wind is straight lines. You can think of straight spaghetti noodles, and it's flowing towards the planet, and those spaghetti noodles wrap around this basketball-shaped planet. And that's indeed what we saw in the data, the magnetic field lines draping around Mars as a planet. One thing that wasn't so expected was the specific configuration of the electric currents that we derive from the magnetic field data. If Mars is a ball here, it's sort of this cup shape on the day side that loops back on itself, maybe something that looks like this. What wasn't so intuitive to me was the directions of those currents and the fact that it wraps continuously around to the night side, and it makes this marvelously complex current system on the night side as well.
This is the first time that we've been able to actually map out the currents. So we can see where the energy is being transferred. We can see what actually forms the underlying mechanisms creating these induced magnetospheres that are not just common here in the solar system, they're 50% of the planets that have them, of the terrestrial planets. And if you want to understand how the atmosphere of Mars and Venus, why they're so different from the Earth, and why they're so different from each other despite both being non-magnetized, we need to understand their induced magnetospheres first.
So knowing how these global current systems are configured teaches us about how charged particles near the planet are going to move, both charged particles in the solar wind and charged particles from the atmosphere itself that are in the process of escaping to space. So now we can understand better where those particles came from, how they move near Mars, and where they're going to go next. That in turn teaches us about atmospheric escape from the planet and the history of the atmosphere over time. How thick has it been? How much has been removed?
It was cool.
Lots of fun.
It was.
Well, hello, everybody. This is Scott Roberts from Explore Scientific and the Explore Alliance, and this is the 14th edition of How Do You Know with Dr. Daniel Barth. Today, he's going to be talking about the doomed moons of Mars, and in fact, I guess the doomed moons of all moons. So that's going to be interesting. Tyler Bowman is with us for a little bit today to talk about the astrophotography contest. Tyler, you want to get started?
Yeah, I'll just go over real quick. Hi, guys. Tyler here with Explore Alliance. Yay. We introduced a new astrophotography contest called the Galaxy Contest. Obviously, it is what it is. It's just galaxies. But just the bread and butter, real quick. There'll be each participant is allowed just 2 entries this time. There'll be first, second, and third place winners. Third place will receive a $25 Explore Scientific gift card or a bump up in their Explore Alliance membership. Second place is $50 with an Explore Alliance gift card or Explore Scientific gift card and a bump on their Explore Alliance membership. First place wins $75 Explore Scientific gift card as well as a bump in their EA membership, and all participants first, second, or third get an 18 by 24 print of their winnings. Now, again, this is for only Explore Alliance members. And if you need any more information on the Explore Alliance membership, you can either go to our webpage and just cycle over the Explore Alliance, or you can email Annie at explorescientific.com, and she will give you any of the information or questions that you have. And that's it for me. You guys have fun about the moons. I'm going to tune in silently.
Thank you.
Tune in silently, huh? Well, that's cool. I have been really fascinated by Daniel Barth's explanations of all the attributes that go into, an orbit, an orbit of the moon around any planet. The barycenter, the effect of gravity, the effect of inertia, all these things that go into it. It's actually very complex and made all the more complex by the fact that moons are either moving in closer or moving in further away, and then what will happen to them? So we have Dr. Barth today to explain more about that. Plus, with a focus on the moons of Mars. So,
Well, thanks, Scott. Welcome, everybody. Glad to see you here again. And so happy that our audience has been sticking with us on this How Do You Know program, this journey. We appreciate you. This is the third of 4 programs. We're going to start out with 3. We're going to go to 4 programs on moons. And this week's program is The Moons of Mars Doomed to Die. It turns out, interestingly, that if you start digging into moons and the way they interact with planets, and we're taught this kind of simple situation. Oh, here's the Earth, here's the moon, and the moon orbits us. And it turns out that it's not nearly as simple as that. There's a lot more going on. We also make assumptions because of who we are as a species. Humanity has been on Earth in one form or another for a few million years. You've probably seen these timelines of Earth from when it forms until today. And I think there's a thing that if all of Earth's history were compressed into a day, humanity appears at about 4 minutes to midnight on December 31st. We haven't been here very long. And we talked about that with the million, billion, trillion program, how much bigger a billion is than a million. And so we think about it, and we haven't been on this ball of Earth very long. The moon, our moon, has been there for all of our history. And astronomy is, I think, perhaps, Scott, the oldest science that there is.
Mm.
We have constellations on clay tablets that carbon date to about 15,000 years ago from the Phoenicians, the Persians, the Babylonians, and in these Mesopotamian civilizations, we can carbon date these clay tablets, and we see recognizable constellations like Sagittarius and Scorpio, and people recognize these, and they were recording them in these clay tablets 15 millennia ago. And yet that shrinks to insignificance to how long humanity has been studying the moon. The henges, the stone and wooden structures built in circular arrays, so you can stand in the middle, and the sunrise and the moonrise will appear between certain parts of the henge at certain times of the year. Primitive calendars, but not a primitive purpose. These calendars for watching the moon and the sun and how it tracks, these are essential for agriculture. And when you're talking about certainly pre-literate civilizations, Iron Age civilizations, you're talking hunter-gatherers who engaged in agriculture. If you screw it up, people die. It's not just, oh, we're going to lose the farm, Ma. It's, gee, if we screw up our hunter-gatherer, now agriculture-dependent society because we've grown, agriculture has allowed our population to grow. Well, if you mess it up, people die, and in large numbers. You can actually destroy your local tribal population if you don't do calendars right, and that depends on astronomy. The moon dwarfs that. These henge structures go back 3,000 to 5,000 years. We think they probably are some that are older, in the 10 to 15,000 year range, although the ones we have date to about 3,000 to 5,000 years old. But records of lunar phases, we have carvings of the lunar phases in a figure 8 pattern. And these are in things like antler bone from deer. And the prehistoric people took the time to observe the sky and record the phases of the moon. And these things are carbon dated to 50 to 75,000 years old. They're incredibly ancient, and they long predate literate, much less written human history. And so astronomy is a very, very ancient science. And for all our history, the moon has been there. The lunar phases have been there. And so there's cultural prejudice that the moon is there forever. It's there today. It's there tomorrow. It'll be there for all time. But in fact, it's not true. And so we're going to dive a little more deeply this week into the science and the mathematics just a bit. And we're going to do this as we did last week. We're going to do this with some illustrations, and we're going to be screen sharing with you. But as you think about this, there's only 3 real facts you need to know. And the first is that when we have a planet and a moon, the moon and the planet interact. And moons raise tides. And so I have my planet, and I have a flat piece of orange clay here. And for those of you that are really technically minded, yes, this is wildly out of scale and proportion. Not in terms of diameter, because tides are very widespread, but if we turn it on the side here and we look, yeah, that's a pretty big bulge. So moons do raise these tidal bulges on planets. They pull on the surface, and the surface rises up toward the moon. Now, on Earth, the tides we're principally familiar with are water tides, tides in the ocean. And tides in the ocean average worldwide about 3 meters, about 10 feet deep. Okay, this is, like I said, wildly out of proportion, but it gives us a good idea. The other thing we need to know is that the tidal bulge, how big is it? Depends on just 3 factors. The first is, how massive is your moon? If your moon is more massive compared to the planet, it has a bigger effect. And the distance between them, and what material the surface is made of. Scott, moons make tidal bulges no matter what sort of material we're talking about. Yes, we have an ocean tide here in Arkansas. We're landlocked. We're a long way from the sea, but
Yeah.
we get tides here. We get land tides. And
Sure.
the rock of the Earth's crust will rise about 2 to 5 centimeters, depending on where you are and what that crust is made of locally. So our rocky crust responds to the moon. And the last thing we need to talk about is when we're talking about a tidal bulge that's big like this in area and 3 meters deep. In our ocean, our tides are billions of tons of water. This is a significant mass. It would make if you took the tidal bulge away from the Earth and you sent it out to, say, the orbit of Neptune, where it would freeze and make an icy moon, it would be a substantial body. It's many billions of tons of mass, and it has its own gravity, which is weird to think about. Oh, tides have gravity? Yes, I have gravity, you have gravity. We talked about this last week. We had the pile of gravel, and we said, oh,
It's got
in
gravity.
space, a lot of asteroids are simply what scientists now refer to as rubble piles. Stone, gravel, sand, bits of material that hold together by their own self-gravitational pull. On a planet's surface, these things fall apart because their own gravity is insignificant compared to a planet. But the tidal bulge is not insignificant. It's big, and it does have its own gravitational field. So the first thing we're going to take you to today, and that's not the right button. There we are. Sorry, I lost you for a moment. We're going to go ahead, and that's the right button. I'm going to share some images for us today. So here's our first one. And yes, I know it's math, but what can I say? So what we have here is Newton's classic equation for gravitational force between two bodies. Scott, don't want to freak anybody out with math, but I just want to point out something. The gravitational force between, say, a moon and a planet, the gravitational force really depends on only three things. M1, how big is the planet? M2, how massive is the moon? And the square of the distance between them. So it's just one mass, two mass, and the distance squared. So when we talk about calculating gravitational force, it's really, really simple. It's just, and G there is a constant, by the way, it never changes. It's just a number like pi that never changes. So we're talking about multiplying two numbers together and then dividing by the square of the distance between. So mathematically, this is really, really easy. It's simple calculator stuff. But when we talk about, oh, okay, let's take a look at, here's how this formula works. There we are. Here's how this formula works between two bodies. And sorry, it's really difficult to get things magnified and stable here. There's our little equation, and here's an illustration of two bodies, M1 a planet, M2 is a moon. What you want to notice particularly here, Scott, the force between them is equal. A lot of people have this idea, oh, the Earth is so much bigger, and it is.
Yeah, so it's going to be more force, right?
It's going to be more force. But Newton's third law, everybody forgets the third law. For every action, there's an equal and opposite reaction. This applies universally.
Okay.
However hard the Earth pulls on the moon pulls equally hard back on the Earth. If it were not true, you couldn't have a stable orbit between them. It would spiral wildly out of control if the forces weren't equal. So the forces here are exactly the same. The force that holds the entire moon in orbit around the Earth, that force raises tides on the surface of the Earth because of the moon's gravitation. And this is kind of a wow thing for people. Like, oh, wow, really? The moon pulls on the Earth as hard as, how can that happen? Well, it happens because gravitation is a reciprocal force, and the two forces, gravitation, are always
Hey,
equal.
Daniel, I think that they're seeing, your screen. Is
Yes.
that right? Crystal
Yes,
clear
yes.
audio, even if the lingo isn't.
Are they not getting audio now? For me?
Zoom hijacked the presentation, so it seems. Let's
Up
see.
here. Let me stop the share and
Okay.
stop the share, and I'll reshare it. Maybe that will help. Because we've
Yeah.
had no problem with this in previous. There, is that better?
Let's see. Now you're good.
Yay,
Okay.
all righty, there we go. So as we can see, again, here's that lovely equation, Newton's equation for universal gravity. And I've made these arrows, force of gravity, Fg, equal size, and because that's physically true. The force, the Earth pulling on the moon is exactly the same. And people don't seem to understand how that's true. Well, let's say we had someone who was big and strong, like an Olympic weightlifter, and me, who's kind of a slim old guy. And we said, okay, here, you take one end of a rubber band, Mr. Weightlifter, and I'll take the other one. And if we stretch the rubber band between us, the weightlifter, in spite of how powerful they are, cannot pull that rubber band any harder than I can. The rubber band pulls equally between us. Gravity works much the same way, and that force is reciprocal and equal. So we get this nice tidal bulge. I'm going to stop my share here. There we go. And when we look, at some point, I've got to figure out how to do a better presentation of slides, but that's okay. Maybe I can have PowerPoint running at the same time or something. But what we've got here is we've got this model that I'm showing everybody where we have this crazy tidal bulge, and we have our little moon here in gray. But most planets are not static this way. Now, interestingly, Pluto and Charon are. We talked about Pluto and Charon last time. Pluto and Charon orbit around each other where the same side each faces the other all times forever. They are completely tidally locked. The Earth is not. The moon takes 28 days to cycle, but the Earth spins much more quickly. The Earth spins in just one day. And so what happens, and I think I can illustrate this here, let's make the orbit of the moon in the vertical plane here. I'm trying to make sure this is lined up. The moon is orbiting this way, okay, up from where we're looking at, but the Earth is rotating this way too. And so what happens is the speed of the Earth's rotation drags this tidal bulge ahead of the moon's position. The Earth is spinning so rapidly. And if you want to think about it this way, you can think about it as if there is friction on the bottom of the sea. And we'll give you this illustration. Friction at the bottom of the sea can pull it ahead. But in fact, it happens with land tides too. So if we're talking about a land tide, the rapid spin of Earth pulls that tidal bulge ahead. And the reason it pulls ahead is that the Earth is spinning faster than the moon orbits. That's a critical point. And we're going to find out that this is a critical point. You realize, Scott, and I'm sure most of our audience does if they think about it, how fast does something go around? Well, it depends on where you put it. Kepler's third law of planetary motion, the farther you are away, the slower you orbit, the longer your orbital period. That's why Jupiter, 5 times farther away than we are, takes 12 times as long to get around the sun once. Pluto's 40 times farther away. It takes 250 years approximately to go around, 248 point whatever. Satellites can orbit faster than the planet spins if they're really close, but most of them that we're familiar with, and certainly we have a bias. We have a bias. This is the only planet we've ever lived on. Our moon is the only moon we've ever seen. And so we have this bias. Moons are far away in space. They orbit slowly. The planet spins quickly, but not all planets are like the Earth. And you can see this diagram here on the screen. The rapidly spinning planet drags the tidal bulge ahead. Now, what's interesting here is that when you drag the tidal bulge ahead, you create a more complex gravitational situation. We had seen a minute ago, oh, we have this situation. Sorry, wrong slide. We've seen this situation where here we go, and the moon and the earth are pulling on each other, and it's very simple. However, when this rotation situation takes hold, we get something different. Here it is, and we realize, oh my gosh, the tidal bulge raised by the moon, the tidal bulge has mass. Mass exerts a gravitational pull, and so we get what we call tidal gravity, and it pulls at an angle. And you're thinking, okay, Doc, how big an angle are we talking about? It's not, for our moon, it's not very big. The tidal bulge arrives about 12 minutes ahead of the moon's position in orbit. I have a link for that in one of the handouts on the series, so you can go, if you're interested in going deep in the math, you can go take a look at that. But even though this is just, this angle in my drawing here is greatly exaggerated, there is an angle. And so these tides are actually pulling on the moon at an angle to the direction that it's going. You realize if the gravity pulls directly in towards the center of Earth and the moon's motion is perpendicular to that, those two things are completely independent. The Earth's regular gravitation here, shown in the big green arrow, cannot affect the moon's speed in orbit because it's perpendicular and you can't do that. It doesn't have any effect, but the tidal gravity does. It's kind of like this, Scott. If this is giving you physics class flashbacks, remember seeing diagrams like this in physics class?
Yes.
Yes. And so these are vector diagrams, friends, and what we're basically looking at. Okay, and yes, another highly artistic diagram by Dr. Barth. So we've got a stick figure here, and they're pulling with a rope, that's our blue line, on this box on the floor. And if you think about it, the rope is at an angle. So we can split this force, we call it a force vector of applied force, and we split it. Part of it goes into, and it actually makes up a perfect triangle here. Part of it goes in the direction of motion, but our rope is not exactly in the direction of motion. Actually, part of it is trying to lift the box up. And you could see if you stood right next to the box and you held the rope at a very steep angle, it'd be very hard to pull. And if you've ever done anything like this, where you've tied a rope to something and try to pull it across the floor, you want to get as low as you can so you can minimize this angle, because you know, oh, if I make it all higher, it's more difficult, makes the job more difficult. So we've got this idea, and we're going to take a look again, and now we're going to tie this back in to our moon. So here we go. Here's our moon. And forgive me here, one at a time.
Okay.
And we realize, oops, here's our tidal gravity. And we realize, oh, this is really, gravity has two components. Tidal gravity, one part of it just contributes, like any other piece of the Earth, to pulling the moon into orbit. It's a straight on gravitational pull, but a very small part of it goes this way. And I'll have you realize, please, that in this diagram, the moon is moving up, okay? As we're looking at it, this would be this little symbol right here would be the Earth's North Pole. We're looking down from millions of miles above. And in this diagram, the moon is orbiting in this direction, the same direction as the red arrow. So we're basically pushing it in the same direction it's already going. We've all pushed a child on a swing set. You wait till the child comes back, and then you time your swing. You don't just randomly shove your arms out here. That's not going to end well. In order to push a child on the swing, you have to wait. They come back and you push, and they come back and you push. The thing is, you always want to be pushing in the same direction they're moving. If you're pushing in the opposite direction, it's going to be like punching the kid in the face. It's not going to be a good day. So this little tidal gravity force is actually pushing in the same direction that the moon is moving. And it's just like pushing a child on a swing. When you time it so that you push in the same direction, you push and the child, higher, higher. We've all done that, right? Child says, push me higher, yay. And depending on how adventurous the child is and how paranoid one of the parents are, but you can see the same situation. There's just two differences between the swing and the moon. With the swing, we're having little pushes every once in a while. The tidal gravity is continuously pushing the moon. The tide is here and it's off, and it's continuously pulling this moon and making it go faster. This little Greek symbol here is a tau, and that's the physics symbol for torque, which is twisting force. And so essentially what we're doing is we are speeding the moon up. Now, if you wanted to demonstrate this for somebody, and I didn't want to do it in my room here because I have kind of a limited space. I used to do this in classroom all the time. You get a bit of elastic cord or a great big rubber band, and you put a rubber ball on one end of it, and you start whirling it around your head. Mm-hmm. And as you spin faster, the elastic expands and the circle gets bigger. The exact same thing happens with the moon. The tidal gravity is constantly spinning the moon up, making it go faster. And if you remember your basic physics, greater speed means greater kinetic energy. And the way that works out for a moon is a physically larger orbit. Low kinetic energy orbits, they may be very fast. They circle the planet very quickly, but they're relatively low energy. If you want to go higher in orbit, you have to fire your rocket engines to accelerate your satellite into a higher orbit. James Webb Telescope is going to be launched sometime later this year. It's going to be put out at the L2 point, 1.5 million kilometers from the Earth. It'll be several times farther away than the moon. And to get it up that high, we're going to have to use rocket engines, and we're going to spiral it up until it hits that distance from the Earth. Wow. So what we're seeing here, Scott, is the moon is a continuously accelerating engine. Now, if we look at this angular acceleration, here we have a little diagram of what happens to the moon's orbit. And you can see there what's happening. The black line represents G, its old orbit. We're putting that torquing force on it, and over time, the orbit gets larger. And that's a fairly simple idea to understand. Mm-hmm. Well, if the moon is getting more energy, we define kinetic energy as basically a product of mass and speed. That's not exactly the equation, but it's close enough. So when we speed something up, we add energy to it. That's why we have to put our foot down and burn more gas if we want our car to accelerate. Go faster, takes more energy, takes more gasoline or diesel or whatever.
Right.
Where's the energy come from? We know that in a car, gas, diesel, electric, the energy comes from the fuel in the car, right? Whether it's liquid fuel or chemical fuel in a battery, that energy is expended and it's turned into kinetic energy. Your car goes faster. So if the moon's going faster, what's the battery? What's the fuel tank? What's the power source? Do you have any idea, Scott, where this energy comes from?
Momentum?
No, indeed.
No.
The energy comes from the Earth itself.
From the Earth itself. Okay.
The Earth, as it spins, it has rotational kinetic energy. And through the tides, it's transferring the Earth's angular momentum, its spin energy, to the moon's rotational energy. So as the moon speeds up and goes farther away, the Earth slows down and the day takes longer. We're actually through
so it's kind of a self-regulating kind of an orbit then.
Precisely.
I
In a
see.
system like Pluto, Pluto and Charon, where the two things always are locked together, there
Yeah.
can be no energy transfer. But because the moon raises tides and the tidal bulge drags the moon ahead and faster in orbit,
Uh-huh.
what you're having without any mechanical linkage whatsoever, separated by 385,000 kilometers, the Earth-Moon system is basically transferring energy from the Earth's spin to the moon's kinetic energy in orbit. The moon's
Interesting.
battery is the Earth's rotational energy. We believe from computer simulations, we know that the moon was created about 4.5 billion years ago. The Earth is about a half a billion years older. The moon was created in a great collision. We call that object, that impactor, Theia. Theia was about the size of Mars. So we're talking an impactor about the size of, here we go. If this is our Earth, we're talking about an impactor about the size of Mars. That would be a bad day. And this Theia object, this Mars-sized object, impacted the Earth. Much of the crust, it was a low-angle collision. A lot of the crustal material was blasted off. The Earth had a rocky ring. The ring clumped up and eventually formed one object, which is our moon. The moon's density is lighter than Earth because only the crustal rock, the lightweight rock, was able to get enough kinetic energy to get into orbit. And we think that at one time, the moon would have been only about 65 or 70,000 kilometers away. The tides would have been enormous, several kilometers high. And the Earth at that time was spinning in about 8 hours. And so we would have had a high tide every 4 hours. That was kilometers high, that rushed hundreds of miles inland. It would have been atrocious. But the closer they are, the more effective the energy transfer mechanism is. And so the moon was spun out. And as the moon spun out, its orbit got bigger and took more time. The Earth slowed down from about an 8-hour rotation over the last 4 billion years, give or take, from about 8 hours to the 24 hours we have now. All that spin energy was transferred into the moon's orbit. So what's happening here? What's happening here is we realize for this moon, that's orbiting more slowly than the planet spins. It's constantly spiraling farther and farther away. It's stealing energy from the angular kinetic energy of the planet and transferring it to the linear kinetic energy of the moon, making the orbit bigger. So providing the planet has enough spin energy, that it's large enough, it's massive enough compared to the moon. If there's enough spin energy in the planet, eventually the moon will spin farther and farther and farther out until one day it reaches that outer Roche limit that we talked about, the limit of stability last week. To where now the gravitational pull between the planet and the moon is about the same as the gravitational pull between the moon and the sun. And then all it takes is a little bump and the moon wobbles off, and becomes an independent thing. This is not good. Now you have two planetary-sized bodies sharing the same orbit around the sun.
Yeah.
Studies, kinetic simulations show that within about 1,000 years, smash, the moon crashes back into the planet, and it's a bad day for everybody.
Yeah.
Good news is, how long will this take? The moon is moving about 1 centimeter away. It will take 5 to 6 billion years for the Earth's moon to reach the limit of stability, and away it goes. Okay, longer than I will be around. Probably will the moon get free in the lifetime of the sun? It's a pretty even bet. Okay. But even if the Earth Moon system is not destroyed as the sun goes red giant, let's say the moon keeps orbiting. As long as it's orbiting, it's stealing energy from the Earth. Even if the oceans boil away, the land tides will still transfer energy to the moon's orbit, and eventually the moon will be lost. Our moon is not permanent. It is doomed to be lost and then very likely reintegrated violently with our planet. Now, it could get a bump from Venus or Mars and fall into the inner solar system. That's the second most likely outcome. It falls in, becomes a elliptical satellite, a planet effectively around the sun. And it may fall in, it may circularize its orbit and stabilize itself. It could, very rare possibility, it could be interacting with Mars and get flung out into the outer and even leave our solar system altogether. But our moon is not a permanent feature of our planet. And go ahead and look at it. If it's clear tonight, it won't always be there. In your lifetime, sure. Your kids, your grandkids, sure. Forever, people don't realize forever is a really long time.
Yeah, forever's forever.
Cosmologists think in terms of how long does it take for a solar system to form? How long does it take for a star to die? What is the lifetime of a galaxy? These sorts of crazy questions. And on these timescales, moons are not permanent. Moons are temporary. So what happens with Mars? What happens with Mars? Let's take a look at a diagram. We don't want that one. We want, trying to make sure I get the right diagram. Let's take a, here we go. It's the, of course it is. It's the one that's orange. So here we go. And I'm going to make this bigger. There we are. So here's a diagram of the moon Phobos on Mars. And you'll notice that I have a little red dashed line there that says Roche limit. And yes, Phobos is currently penetrating. Remember, orbits are all elliptical. Kepler taught us that. Aristotle's little obsession with perfectly circular orbits was delusional. All the orbits are elliptical, and no, I didn't quite draw it that way. I simplified the drawing a little bit, but what's happening with Phobos? Like Io, we talked about Io last time, flirting with the Roche limit. Phobos actually dives inside it. Phobos is in the process of being disrupted. It's tidally stretched, and if you look at pictures of Phobos, you can see these great long fractures in the crust that are happening from the stretching process. Phobos is in the process of being destroyed. And you can see that our diagram here is different. Notice something here, Scott. Look at the rotation.
Yeah.
And look at the tidal bulge. Phobos is ahead of the tidal bulge.
Yeah. Because it's going
Phobos,
so fast, right?
It's spinning faster than Mars spins. It's orbiting faster than Mars spins. Mars orbits in 24 hours, 37 minutes, something like that, very close to Earth. Phobos, Phobos takes about 9 hours to go around once. It's going so fast that we would actually see it rise in the west, set in the east. And it crosses the sky 3 times a day. It goes through an entire cycle of phases in about 7 hours, which is completely bananas.
So Daniel, does Phobos overtake its tidal bulge at any time?
Keep in mind that Phobos is raising the bulge. So
right.
No, it does not.
Okay.
But it's always ahead of it.
So he's ahead of it. So it's dragging it behind it.
Yes, precisely right. You are precisely right. And let's take a look at the next diagram. And here we are. And we're going to stretch this out and make it as big as we can for everybody. And of course, on the handout, friends, if you're in the audience, the handout, I hope you'll download it from theexplorescientific.com/how do you know.
Yeah.
Because
I put the link here in chat so people
exactly.
can.
It has the entire discussion of this with all these illustrations. They're in there for you to study at your leisure. We see here that for Phobos, that torque vector, that force is now pointing backwards against the motion of the planet. And it is not the fact that Phobos is inside the Roche limit that's causing it to slow down. It's simply the fact that it's orbiting faster than Mars spins. So what's happening now? The tidal gravity, it's pulling backwards, slowing the moon down. As it slows the moon down, and its linear speed slows. As it slows, oddly enough, the orbit shrinks and its orbital period gets much faster. But that's an interesting bit of math. But basically, it's going more slowly. It's spiraling in toward the planet. When it gets close enough, Phobos will be disrupted. It will become a rocky ring. Now, there are some very interesting speculative theories. And you know what scientists do, the dynamicists, they go and they set up, they can't fly to Mars, so they model it in a computer. There are models that indicate that what happens with Phobos is that it spirals down in, it gets disrupted,
Okay.
and then it reassembles itself. We know the Earth's moon assembled itself gravitationally out of a ring of stone. It
Okay.
reassembles itself. In the process of reassembling itself, it flings itself out a little bit farther. And so there are people who predict that Phobos goes through a cycle of spiral in, disruption, reassembly, flung back out, spiral back in, and it sort of yo-yos in and out.
It just keeps doing this process.
So how do you test this? If we could go and get some core samples from Phobos and do radiologically date them. If Phobos is on the order of billions of years old, and we think Phobos was probably, we don't think it's an asteroid. There are a lot of bits of evidence that says, no, it's not an asteroid. It's probably a piece of Mars. Mars got whacked. We know the Noachian Basin, the Great Northern Basin. We know Mars has been smacked a lot, just like the Earth has, like all the planets have. So Phobos is a remnant. Well, every time it disrupts and it reassembles, guess what? The radiological clock restarts. So if we get core samples and they're several billion years old, Phobos is on its first trip through the Roche limit. But if the other dynamicists are correct and Phobos goes through this destroy and reassemble cycle, then these core samples won't be more than a few 100 million years old. They'll be much younger. So NASA has plans, ESA has plans. There are lots of ambitious people with missions on the drawing board. Let's go to the moons of Mars and collect a sample and return it to Earth. Okie doke. Sounds like a fun trip to me. I'll go. And it would be fascinating to be on a really low gravity moon where you have to be careful because on Phobos, you could literally ride a bicycle off a meter high ramp like these kids do in skate parks and launch yourself into orbit. It would be very hard to walk around on Phobos. And tripping and falling would be bad, would take you a long time to come down. So we want to gather these samples and see. So Phobos is in a process of spiraling in. Phobos is doomed to die. Whether it's going to die once and form a ring and then basically be eliminated as a long series of meteors over millions of years, or if it's going to destroy and reassemble each time, it's like the whole thing collapses and gets ripped apart. Phobos is doomed to die. Now, what's interesting is if we take a look at Deimos, and here we go. Here's the two of them. Here's Phobos and Deimos. And I'm going to blow this up as much as I can. There we go. Now, here you notice, Scott, we have two dotted lines.
Mm-hmm.
The inner red one is the Roche limit. That's how close you can put a moon on Mars. Any closer than that, as we talked about last week, the moon is disrupted. It becomes a ring of particles. People seem to think if the planet's gravity is sufficiently weak, the moon will reassemble. If the planet's gravity is really strong enough, it never does. That's the difference between Saturn and Saturn having a ring and Earth having a ring after the Theia impact. Earth's ring reassembled into a moon because Earth's gravity is relatively weak compared to the self-attraction of the particles in orbit. Saturn's gravity is really powerful. And so they are constrained in their orbit much more, and they cannot reassemble. So here's our Roche limit, this red line, but here's a green line. That green line is called the synchronous limit. On Earth, we call things that fly here geosynchronous satellites.
Right.
You know, they're used for weather satellites, military research, climate research, all sorts. Why? Because we know that the farther out you go, the slower you are. In here, Phobos is orbiting much faster than Mars spins. Out here, Deimos orbits slower than Mars spins. But on this line, the orbit is the same amount of time as Mars spins. On Earth, this is about 24,000 miles, about 60,000 kilometers. If you put a satellite there, it just hangs over the same spot on Earth all the time. It goes around the Earth in 24 hours. The Earth spins in 24 hours. And so this satellite just stares down at one place. If you want to track hurricanes across the Atlantic, this is the bomb. If you want to put up a satellite and, you know, spy on your geopolitical neighbors, that's the great place to put the satellite. It's also really far away. It's hard to reach with an anti-satellite weapon. But for our purposes here, this line, moons that are outside of it orbit more slowly. Deimos, and I'm hoping I'm saying that right, not a Greek speaker, sorry. Deimos orbits in about 30 hours. Mars spins in about 24. So Deimos, as I've drawn here, it's always behind the tidal bulge. Like our moon, it's accelerating. It's spinning away. It will eventually reach that limit of stability, the second Roche limit, and it will spin away and become an asteroid indeed. Phobos is inside this green line. It's inside the geosynchronous limit, and so it's spinning faster than Mars, and because it is, it's always spiraling in. So the clever pundit might ask, well, couldn't we have a moon orbiting exactly on the geosynchronous line? Well, I suppose theoretically you could, but there's that one little catch. The geosynchronous line is indeed a circle because planets are, to all intents and purposes, a sphere. And this is a line established by gravitational attraction. So the geosynchronous line is a sphere, orbits are elliptical. Even if you put a moon, you could wave your godlike wand of power and put a moon exactly on the geosynchronous line for any planet. The elliptical nature of the orbit, different distributions of mass. No planet is completely homogeneous, like my ball of clay. They have different mass concentrations. These little things disturb the orbit and make it more elliptical, and it's either going to eventually fall inside the line and spiral in to the Roche limit and be destroyed, or it's going to fall out from that geosynchronous line and fall behind the tidal bulge and be spiraled away to be lost in the depths of space. Maybe re-impact, maybe not. But there is no such thing as a permanent moon. Moons are temporary structures. We have this cultural, perhaps species-wide preconception that our moon is a permanent fixture in our sky. But it is not. We know that we have marks on the moon. We have marias and craters from impacts. The moon changes. We've seen impactors on the moon in real time. We've seen impacts on Mars that have happened. The Mars Global Surveyor has circled around taking these high-res images of Mars. Ooh, look, a new crater. An asteroid has hit Mars. So we know intellectually that surfaces of planets are not permanent. Surfaces of moons aren't permanent. Guess what? This is kind of an expansion of the Copernican principle. You probably remember the Copernican principle. Before Copernicus, there was this whole mishmash where astronomy got co-opted by the early church as a tenet of faith, eternal and unchanging. Galileo warned the Pope and he said, don't do this. Science changes. Faith is supposed to be eternal. Science changes everything. It's not permanent. Copernicus comes along and he says, oh, guess what? We are not the center of the solar system. And the Copernican principle is, if you're doing any kind of research and you come up with this idea that something is in a specially unique place or a special unique time, you're wrong, because the universe is very vast and there is no center. There is no preferred place. Einstein confirmed that. There is no preferred center of the universe. Mach did this.
Shapley,
no preferred
Carlos
place.
Shapley. No, we don't even occupy a very special part of the Milky Way.
Correct. And Hubble found out the Milky Way isn't everything, right? It's
right. Yeah,
It's not an island universe.
Just another of billions of galaxies.
And so this Copernican principle comes along again and says, oh, you think your moon is special? You think your moon is forever? Don't be silly. Of course it's not. Moons are all doomed to die. They'll either spiral in and be shredded by the Roche process, tidal disruption, or they'll slowly spiral away. Their planet will effectively play crack the whip. Did you ever do that when you were a kid, Scott, skating?
Crack the whip?
Oh, yeah, we used to do this.
I used to have a bullwhip.
No, we used to do this in Wisconsin. You get out on the lake with everybody on skates and you get a line and everybody would start circling. And of course, the inner kid is just barely turning, but the kid 8 or 10 or 12 people out is really moving, and eventually you just let go and you're...
We lived in a poor neighborhood. We couldn't afford skates, but we would still crack the whip with just running. And
just running. There you go. It's the same thing. So we get this idea that all moons are temporary. So when we come back next week, I received a question from a teacher, and we're reaching out to him. We hope he'll be a guest with us next week. And he asked a very interesting question. How many moons does the Earth have? And what's the definition? I've been looking. What's the definition of moon anyway? And Scott, I'm hoping you can see here. I'm moving my camera a little bit.
Yeah.
Here's this lovely pile of textbooks.
There's stack of books there to kind of answer that question.
I've been teaching astronomy for about 40 years, more than 40 years. These are all textbooks I've used. None of them have a definition for the term moon. So moon is it an undefinable thing like 0 divided by 0 on a calculator? We're going to, in the next episode, see if we can't come up with a modern definition of moon that makes sense and answer the questions, how many moons does the Earth have and where are they anyway? So that'll be next week on How Do You Know?
Great. Daniel, you've been getting some very nice comments from the audience here and a few questions here. I'll read some of them. Pekka had asked a question, apparently maybe last time that you were on. He wanted to know if we had figured out about a tsunami caused by a slowdown in the rotation of the Earth caused by, let's say, a huge asteroid or comet flying past Earth. Is that a possibility?
It is a possibility. It would have to be something very, very large. Let's put it this way. The planet killer or the dinosaur killer, the Chicxulub impact, 10-kilometer, 7-mile wide asteroid, that would not be large enough to cause the kind of tidal disruption she's talking about. You would need something
Texas
I mean,
sized or something.
yeah, you would need something the size of Ceres,
Oh,
5 or 7 or 100 or 1,000 kilometers. And if it went really close, then yeah, you could actually get the gravitational disruption would be enough to cause continental plates to suddenly shift, and you could get tsunamis. Um, it would be a bad day if
be a
Ceres
bad
came
day. You'd have to
within.
repolar align your telescope. That's
Yeah,
for sure.
yeah. If Ceres came within, I'm doing quick shoot from the hip, but
Yeah.
if Ceres came within, say, 10,000 kilometers, it would be a bad day.
Hmm.
Probably farther out than that, because these gravitational effects. Remember, it goes by the square of the distance. So if you talk about something twice as close as the moon, 4 times the effect. 1/10 the distance that the moon's at, 100 times the effect. So I suspect if you got something within 10 to 25,000 kilometers the size of Ceres, it's going to be a bad day, and a lot of people would die. So yeah,
Yeah, we don't need that.
that's maybe a horror movie, but not that kind of stuff.
We don't need that. Let's see. Okay. So let's see. We have more here. Clear Light 58 says, where I am, I look out at a tidal marsh. I watch the effect of gravity every day. Sometimes it keeps us from diving into town, or driving into town, not diving, driving into town when we have an astronomical high tide.
Oh, so if they have spring tide when the moon and sun are lined up,
Yeah.
they get the tides come in and floods their roadway. Yes. There was a great book about a huge springtime flood in the Netherlands called A Tide in the Attic. I remember reading it when I was a boy. And it was a story about a great flood that occurred at a spring tide, and was much higher than normal.
Clear Light goes further on to say, he says, we have a tropical storm coming up the coast and an astronomical high tide about to happen. We will get coastal flooding for a few days at high tide.
Yeah, the sun's gravitational effect is about the same as the moon. So when they line up at spring tide or neap tide, that's one is new moon, one is full moon. And I think the spring tide is the new moon. Then the earth and the sun and the moon are both and aligned up on the same side of the earth. Then you can get effectively double the tidal flow. You're talking going from 3 meters to 6 meters. And I'm, certainly any extra flooding is bad. And I don't mean to minimize your situation.
Right.
But I'm hoping that it's not as catastrophic as perhaps the breathless announcer on the Weather Channel maybe has made it seem. Certainly prepare. Don't stay in an area that's about to flood. Flee the tropical storms.
Go for high ground.
Go for high ground. I don't mean to minimize this, but I'm hoping it's not as ferociously terrible as maybe you're afraid it might be.
Yeah. Yes. Clear Light further comments or asks, I wonder if that theory of the collision with Earth comes from where the planet's current orbits are. Other than geology, how would we know that that collision happened?
That I want to thank Clearline 51. That will make an excellent entire How Do You Know program. And we'll put that on the schedule soon.
Okay.
The origin of the moon and how we know. In fact, I will answer part of your question right now. It has very little, nothing to do with the orbits where they are now, because the moon was formed about 4.5 to 5 billion years ago. And we don't have the mathematical precision to trace the orbits of planets that far back with any reasonable accuracy. We, in fact, know about the Theia impact from physical evidence, primarily from the Apollo missions and other moon research missions from the ESA, Roscosmos, and of course NASA in the eras since 1969. But I think that would make an excellent How Do You Know program, because that's really a fun topic that deserves a more complete answer. So we'll put Clear Line 51. We'll put your idea into the schedule for a program in the upcoming weeks.
Great. Okay. Book Davy says, well, eventually Phobos will make a nice Martian crater.
Actually, lots of them, because it'll be disrupted. It won't hit as a body.
Yeah, it'll be a shower.
It'll be a shower. So lots of new craters, big and small, circling the equator of Mars. By the way we know Phobos and Deimos are not asteroids, their orbits are very circular, and they're almost perfectly aligned with Mars' equator, which would happen for an ejecta from a big impact, but asteroids would be captured in a highly elliptical orbit, and they can be randomly oriented depending on what part of the ecliptic they come out of, but ejected material almost always has this perfectly circular or nearly circular orbit that's lined up nicely with the equator. The moon is also, our moon is lined up with our equator. It's tilted only about 5.5 degrees. And that's one of the bits of evidence that indicate to us that it was a collision and not a capture.
And Mike Wiesner comments, this is my question too. He says, I'm not a geologist. Why does the radiological clock reset with Phobos reformation?
The disruption generates a lot of heat, and the interior will melt as it fragments. And molten materials, their isotope ratios are free to mix, but once they solidify, then their ratios are fixed, and they start to generate decay products.
Decay starts all over again. That's
right.
The
generation of decay products in newly formed minerals starts over from scratch. That's the short and quick 30-second answer. That, again, we could take a whole program, and that's kind of a bit outside of our astronomy wheelhouse. But yeah, we could do that. But when minerals get disrupted and then they remelt and reform, their entire radiological clock gets reset to zero.
Okay, we have Adrian Bradley watching from Belleville, Michigan. Egon Reich says, another great show. He's out there in Southern California.
Thank you.
Andrew Corkill in Southern California. He says, this morning I was looking at Saturn with binoculars and saw at least 10 satellites pass through the field within 15 minutes. Alluding, I guess, to Starlink. Yeah. Armando Lee, he's watching from the Philippines. Awesome concepts being shared here. Thank you. Thank you for this program, Explore Scientific. Book Davy says, I forget how many there are planned, but he's talking about the Starlink again. Starlink has questions, I guess, for all of us,
Yeah, Google has a set they want to send up, Amazon, as well as Elon Musk, Starlink.
And we're not the only country that wants to do this.
China is doing a satellite constellation, and each of these groups, there's a group in Britain, and they're each talking between 10 and 30,000 satellites. So we're talking about the number of satellites going into the 100,000 range before the decade is out. And that will be very disruptive.
It'll look like fireflies in the sky, I guess.
Kind of, yeah.
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 Clearlight says, even for us older folks, you are never too old to learn new things. This is not just for kids.
No.
That's right. Well, we're all kids, right? I mean, come on.
I'm a kid at heart. I'm an old bald guy, but I am a kid at heart. Ask my wife, ask my boys.
That's right. Andrew Corkill says, Dr. Barth is really well spoken and great to listen to. These are concepts that nobody really knows. All moons are temporarily phenomenon. I've never heard of that before, and so clearly.
Thank you.
Right.
That's high praise.
This is the
someone comes to hear you speak and says, "Wow, that was really clear. I get it." That's about the.
That's it.
That's
right?
the best.
Yep.
That's the
Clearlight wants to know: has anyone ever calculated when Phobos will start breaking up, and diving towards the planet.
It's
If we are
happening
thinking
now.
of building bases there, it seems like a good question. Or are we talking millions or billions of years?
Phobos is breaking up now. You can take a look at images of Phobos and you can see these long rift lines. And you ask yourself, what would cause this? And it's this tidal disruption. I think Phobos is probably stable in the 50 to 100,000 year time frame. Roche disruption is a slow but exceedingly thorough process. You've heard the wheels grind slow but very fine. Sometimes we talk about that with justice and other things, but the Roche limit does that too. It grinds slowly but very fine. Certainly in the time scale of human building and constructs, even like the pyramids. Oh, we built the pyramids and they're still standing 3,500 years later. There you go. There's Phobos with its
Right.
great
Look at that.
variations. Yeah.
It does look stretched, and look at the
Yes.
repeated impact marks, like in
Yes.
rows and stuff.
Chain craters.
Yeah.
Yeah.
And plus
Yeah,
that
these,
giant crater right there.
Yeah,
It
that's
looks like a
sticky.
football. It's been bashed in on the end, right?
Yeah, it is. Phobos is the Death Star. It has, that was the inspiration for George Lucas and the Death Star, because it has this gigantic crater on one side. Even in terms of if we built something to last 5,000 years, we'd be safe putting it on Phobos. Again, when we talk about timescales, it's important to draw a distinction between astronomical timescales in terms of the solar system, cosmological timescales in terms of the life of a galaxy, and human engineering timescales in terms of decades, centuries, millennia. The pyramids are still standing, and we could build one on Mars today, and 5,000 years hence, it would still be there. Ultimately, it would be torn apart. But then again, if you think about it, continents drift too. So anything that's above the ground now eventually goes under in a subduction. So even bits of continental plate are doomed over those kinds of timescales, because the Earth's crust is recycled in subduction events, and they're not pleasant. That's what caused the tidal wave that destroyed Fukushima. And Aceh, Banda Aceh in the Indonesian archipelago, around 2004.
Yeah.
Killed 200,000 people.
Yeah, it's terrible.
They had a big subduction event, and they said, that subduction event was big enough to change the Earth's period of rotation by a measurable few thousandths of a second. These kind of events where you do have big subduction shifts that cause tidal waves, they do affect Earth's rotation, not its angular momentum, that's conserved, but its rotational period, yes. And these subduction events actually, because remember, there's outgrowth events. The Atlantic Rift is a place where there's seafloor spreading. So essentially the crust is getting stretched larger, and then it's at subduction events,
it's being
it
squeezed.
snaps back, right?
Yeah.
So the rift is actually stretching the Earth like a spring, potential energy, and then we get kinetic energy back when we get that subduction snap. And nature rolls over in her sleep and people die. These events, which are minuscule, you look at the amount of change, because as the Earth expands and gets a larger circumference because of rift spreading, it's like a skater spreading their arms, they slow down, and when they tuck their arms in, they spin faster. We've all seen this in professional skating. Well, and gymnasts, well, guess what? The same thing happens with the Earth. So if the Earth rotated faster, it's because as the rift spreading enlarged our circumference, we slowed down. And so all these things are conserved, but sometimes the tiny little respect to the Earth, tiny little jumps and creaks and snaps and pops, they aren't so tiny for the little beings living on the surface.
Jeez.
So there we go.
Okay, and let's see. We have Armando Lee from Philippines saying, Daniel, you really explained these awesome concepts so well and made it so simple to understand without going into too much jargon.
Thank you. I
Very
hope
nice.
you'll share these with some of your friends. I hope all
Yeah,
of you
that's
will.
right. Billy's
Share these.
Astro is kind of digressing just a little bit, but still about something that's orbiting. He's wanting to know about the wooden satellite that was mentioned in the news recently. So we'll find out if wood actually can withstand the environs of space. So
I don't see why not.
yeah, it's
Um,
looks like a little CubeSat made out of
Made out of wood.
wood plates or something.
Wasn't it made out of bamboo? I'm thinking I read something about that.
Was it?
You know what? I'm shooting from the hip here, and I don't mean to be disrespectful
find
to
out.
our audience's questions. We'll see if we can investigate that. And again, it's
plywood.
an experiment.
It's plywood.
It's plywood. Okay,
Yeah.
so it's probably
And
birch.
it has, I don't think it's out in space yet. It'll launch
Okay.
this year.
It's almost
Yeah.
certainly birch plywood.
Yeah. It was
And
made by Arctic Astronautics, a Finnish company manufacturing
it's
CubeSat
going to be
kits.
birch.
Yeah.
Yeah, it'll be birch plywood, and I see no reason why it wouldn't. Metal gets metal fatigue from radiation. We know this in practical sense because of HELLO reactors, and we found parts in reactors that get brittle and break because of radiation. I suspect that wood, with its cellular structure, would be able to withstand damage more
Right.
than metal might. So, and certainly it'd be cheaper to get into orbit because it's lower mass.
Right.
Engineering material science is all about picking the material that has the right properties for the job at hand. Lightness, flexibility, durability, resistance to abrasion. All of these things vary. That's why we have metallurgy with all sorts of different alloys. And plastics, much the same. We engineer plastics the same way. But for many things, natural materials, not only are they renewable resource, but there's a surprising reason why we built and designed materials with them for millennia. All of Kepler's things were wood and stone. Very little was metal. The hinge points and the bolts, but essentially the great quadrant on the side of a building was a wooden structure mounted onto stone. There was somebody just saw a piece in a newsfeed. Somebody was rebuilding Kepler's quadrant engineered out of wood, trying to redo some of his observations. And it's not simple. You realize the things that people like Kepler and Brahe and Copernicus and Galileo did with the equipment that they had. Their mathematics were relatively sophisticated, but their equipment compared to today was quite primitive. Galileo would have been beyond stunned at the quality of the most basic
toy telescope today.
Toy telescope.
Yeah.
And you talk about something like an 80 millimeter refractor or a 4.5 inch Dobsonian.
Yeah, that would have absolutely blown away the whole world.
Absolutely,
it would have been the world's largest telescopes at the time.
At the time, it would. Yeah.
Yep.
Yeah, Huygens did a lot of work with a 6-inch reflector of his own design and manufacture, and it was at the time the largest scope in the world.
Very cool.
So yeah. Well, this is great. I'm so glad to have questions from the audience and comments.
Let's see. Anything
really,
else?
Thank you, folks. Really.
Yep. Martin Eastburn. Martin says, I might have some military books from Dad that might have the moon definition. Also have government printing office from the Naval Observatory research.
I looked at research for next week's program.
Yeah.
I went online and I said, give me the 20 best dictionary websites. And so I went looking, and you'd be stunned at how many of them had errors.
True.
And it was just terrible. And then I'm like, and that inspired me I've got all these. You can see in my. This isn't a background here. This
Yeah,
is
you see that all that stuff behind him?
That's my
That's other
one
background.
of, I have 3 libraries in my
Plus
home.
the internet.
Yeah, this is one of 3 libraries in my home. This is my technical library.
Uh-huh.
I have a art and fiction library in the room next door, and then we have a film library with about almost 5,000 titles.
Jeez.
But these are books that I've taught astronomy with, and reference books from classes. And I'm starting to look. One of the things I would do to students when I was teaching astronomy, I would give them a vocabulary list. I'd look up the definition of the word planet. And this was before the IAU.
Okay.
Pluto's not a planet nonsense. That's another program. There's no definition of planet. And he said, what the heck? Teacher, what's going on? How come there's not a definition of planet? I said, well, it's a very ancient colloquial term. It's almost like slang, yo. And because it's colloquial and it's ancient idea, science has changed, transformed, and redissolved and reformed itself many times since the word was
much like the moon of Phobos, right?
Right. Planetes, the Greek, wandering star. How far have we progressed from there? And so planet is not well defined. Even today, I'm going to be a science heretic. I reject the IAU definition. I still say planet is not well defined. Not that it's undefinable, but that it is currently poorly defined. And I do believe the current definition will end up on the ash heap of history, like Harry Star for comet.
Sure.
And
That's science. That's science.
That's science. And next week we're gonna plant our flag on that hill, and we're gonna properly define moon for you. So I think I've nailed it, and I'll leave it to our viewers to decide whether or not they think I've nailed it.
All right.
It's going to be an exciting program. Be sure to tune in, friends.
That's right. All right, Daniel. Well, thank you very much. What's that?
Dr. Barth takes on the establishment.
That's right. We're going to have one side, the IAU team, whoever they are. Okay. And on the other side is just you.
Gonna whoop them.
You're going to whoop them.
Gonna whoop them.
So you heard it on this show first. Daniel Barth is
right.
calling out the IAU out to the schoolyard flagpole. Okay.
I have a strength of 100 men because my cause is just.
Okay. Well, great, Daniel. Thank you so much.
Thank you,
hope
Scott.
you guys enjoyed the show.
Thanks,
I see that you did, of course. And Daniel will be on next Monday. So,
and you all are welcome to write to me if there's a question you didn't get answered. astronomyforeducators@gmail.com. I answer every email I get, at least the serious ones that aren't all flat earth weird and stuff. So
right.
If you have a question, then please email me, and happy to take on the challenge. Stump Dr. Barth.
That's right. That's right. Okay. Well, thanks, everyone. We'll see you
everybody.
Tomorrow with another program of the Open Go-To community. This week also, we've got Cameron Gillis coming back on for Cam Astronomy. We have the 51st Global Star Party happening Tuesday night, starting at 8 o'clock. So you're going to see some people shuffling around a little bit, but we still have a great lineup, as we always do. The 52nd Global Star Party, which is towards the end of the month, lands on the same day as the birthday for George Ellery Hale. Okay, well, this guy has a mountain named after him. He has an asteroid named after him. He has a crater on the moon named after him, and a crater on Mars named after him.
Yep.
He built in succession 4 of the world's largest telescopes in his lifetime. He invented astrophysics. He is the original publisher of the astronomical journal, or the astrophysical journal, the APJ. He starts the American Astronomical Society, which is still going strong today. He is, for the AAS, I believe he is recognized on a medal given away for solar research. He still affects astronomy to this very day. And so on this, I think it will be his 153rd birthday, something like that. We're going to celebrate it. So I'll be trying to pull out some special guests for that one. So
I will make a prediction that one day there will be a city on Mars named Hail City.
that would be a good one. That's right. That's right. Well, until tomorrow, you guys have a great night and keep looking up, and we'll see ya.
Bye-bye, everybody.
Hello, everybody. This is Scott Roberts from Explore Scientific, and today I want to talk about the world-famous Galileo Telescope Kit. This is a kit that you assemble by yourself. You'll learn how optics work by assembling the objective lens and also the eyepiece. And there's two different eyepieces that are in this. It's a 25 power, 20 millimeter eyepiece, but it also comes with this very clever little device here that works both as a Barlow lens that will double the magnification of this eyepiece, making it 50 power, or it can be used also as a Galilean eyepiece, which gives 17 power to the telescope. This is what Galileo virtually saw through his own telescope. So you can have that same experience that Galileo had looking at the moon, looking at Saturn's rings, looking at Jupiter. It is a telescope that was designed for the International Year of Astronomy in 2009, and it's a fantastic kit, both for child and adult, to learn how a telescope works. And so if you get the telescope like this, you can either have it on a stand like this, you can hand hold it like a pirate's glass, or on the bottom here, we have a thread-in hole here that you could put it on a camera tripod. Very versatile, very rugged, and a lot of fun, all from Explore Scientific.